Hello class, this is our lesson for 2.1, Polynomials to model the volume of a box. So I've got a flat piece of paper, and it talks here about in 6th grade possibly you learned this volume formula. Now instead of being given a box and just finding the volume, we're going to be given just the idea of a box basically and variables, and we're going to come up with a bunch of different equations for volume that could happen. So what we look at is we look at having a piece of paper and cutting a little x-shaped corner, x by x square, out of each corner. And then after we cut out those little squares, what we would do is we would fold up the sides, right? So I'd fold up the side here, I'd fold up the side here, I'm folding them all up. And so I could end up with some kind of box that my height is going to be that x, and then this would be my length, this would be my width, right? Or other way around. But my height, the part that's folding up, is going to be x. So I could fold it up like in this picture. It looks like a little tiny square that they cut out of the corner. I could also cut out like a really big square out of all of the corners, right? And that would make a different shaped box. That would make a box that's a lot taller, but not as wide and not as long. So we're looking at creating an equation that kind of allows for all of this to happen and to think about all the different volumes that we could get. This is a problem that you're going to see in Algebra 2 and pre-calc and calculus. So we're really interested in having an equation for something like this and then maximizing it. And we'll get to that later. So I want to erase all of the scratch work I made over here just so we can kind of work through the algebra of what this equation would look like. This is something that you're going to be seeing all unit. So we start out by thinking about volume equals length times width times height. So our height, the part we're folding up, that's going to be the x part. We've already looked at that. So for my width, that's going to be one of our dimensions of the paper. So I'm just writing down one dimension, and I'm going to call it D1. That's what I'm going to call that dimension. So that's going to be this part right here. And then because I'm cutting out a little x bit on both sides, I'm going to have to subtract 2x. For the length, I'm going to use the other dimension of the paper. And so I need something else for that. It's not the same, so I'm going to call it D2. They could be the same, but they don't have to. And again, if this entire side is D2, but I'm cutting out this little bit of x on both ends, then I have to subtract 2x. So then let's think about how to write our equation. So if I think about length times width times height, my length I have as D2, but I'm subtracting the 2x's out. So like this part here, from here to here, is going to be D2 minus 2x. And that's the actual, like this part right here along that box, right? And then when I'm looking at my width, it's not the entire D1, right? We said it's the D1 minus the 2x. And then my height, I've already decided I'm using x. Those are my three dimensions. Those are my length times my width times my height. So in order to write an equation for volume, I would say my volume is x times D1 minus 2x times D2 minus 2x. That's how I'd write that out. So if we have actual paper, right, if we have a dimension that's 3 and one that's 8, we'll just make these guys D1 and D2. Then all I would have to do is substitute those values to find an equation. So my volume would be x times 3 minus 2x times 8 minus 2x. The next step is finding a domain. So remember, domain is all of our inputs. It's, in this case, our x values. So what kind of values can we have? So we know that cutting out squares with side length less than 0 does not create a box. So I can't cut out a negative value. And even with 0, it doesn't work. If I don't cut out anything, I just have a flat piece of paper. I have nothing to fold up. So 0 has to be less than our x. Now, what's the biggest number? The biggest number is that if we went all the way and cut this box right here and cut out this giant square on this short side, now there wouldn't be anything left to fold up. The whole side would be gone. That would be the absolute, like, we could leave a tiny little sliver of paper there, right? But we can't cut that much out, that whole side is gone. So that's to find the maximum length. We would start with our short side. And then because we'd be cutting out a square of both sides, we would divide the short side by 2. Maybe I should say shorter because both of them might be short, right? So let's add shorter side. This is the end of the domain, not included, okay? So that's the number we'd put over here. So I'm going to call it, it's either D1 or D2. I'm going to say it's D1. So D1 divided by 2, where D1 is the shorter side. So if we think about our previous example, my shorter side was 3. So 3 divided by 2 would just be 3/2, or it could be 1.5. So my domain would be 0 less than x less than 1.5 or 3/2, right? We could write either one of those. Usually I have you guys write fractions, but for something like this, 3/2 might be a weird volume. It might make more sense to use decimals. Okay, so we are going to try this now. New piece of paper, cardboard's 15 by 24. We're going to find the volume equation and the domain. So my volume, I know I make x times one of my dimensions, 15 minus 2x, times my other dimension, 24, minus the 2x again. That's my volume equation. My domain equation is going to be 0 less than x less than, and then I've got to think about the biggest amount we could cut out that would result in no more things to fold up anymore, and that would be taking my shorter side and dividing by 2, which is 7.5. So 0 less than x less than 7.5. And this would be in inches. We really should write inches here. All right. Now, looking at a volume graph. So identify the domain by looking at the x-axis, right? Find the value of x for when the volume is maximized. Those are the things we're trying to do. If the graph crosses through the x-axis and continues after, those values are not in the domain and should not be used. So let's think about what happens. When I look at this part of the graph down here, this is below my x-axis. Here's my x-axis right here. So if I think about how y, when I go up it's positive, when I go down it's negative, this is where it's showing my volume is negative. And I know that that's not possible. So anywhere below this x-axis doesn't make sense, okay? So my domain is going to be between those two x-intercepts. That's what's going on here. So my domain, the part of my graph that's actually usable, is from, it looks like 0 to all the way over here. And I've got to look real close to see if it's a 15 or a 1.5. And it looks like a 1.5. So again, it can't actually equal 0. So we're going to just say 0 is less than x is less than 1.5. Because both of these are on my x-axis. Think about that ordered pair 0, 0. Think about the ordered pair 0, 1.5. So this is saying, other way around, 1.5, 0. I caught myself right away. 1.5, 0. So both of these are saying that this is the amount I'm cutting, this is my x, and this is my volume. Same thing here, I'm cutting out a square that's 1.5 on both sides out of each corner, and it yields a volume of 0. So a volume of 0 doesn't really make sense. I can't have a 0 volume. That's why I'm not making these or equal to in there, okay? So that's why it's just 0 is less than x is less than 1.5. That's going to give me a volume. Now I want to think about when my x value is happening, and this is for maximum volume. So if I think about where I have maximum volume, that's this point at the top right here. So I need to figure out the x value that corresponds to. That means I got to trace this down to my x-axis here and try to figure out what it is. Actually, it looks like it's more like in the middle of this box over here. It looks like about 0.65 to me. The book says 0.63. Those are both, I just know it's in the middle of the square between the 0.6 and the 0.7. So I'm going to write x as approximately equal to, and I'm going to use my 0.65, but in parentheses I'm going to write actually 0.63. And so if you draw that line, if you're really careful how you draw it, it comes kind of down into the middle of a box. And you know that the box is 0.6 on one side and 0.7 on the other. So that's when my volume is actually happening. It's happening when I'm cutting out a 0.65 square out on both sides. Now, what is the actual maximum volume? So the maximum volume I would get by tracing across over here. right? This is where I get my maximum volume from. And it looks like almost halfway exactly between the 7 and the 8, maybe a little bit under. So I could call it 7.5. I could call it like maybe 7.3-ish. Oops, I made that really, really big. So I'm going to say my maximum volume is about 7.3. So remember, this means V of 1 point, or actually what was that? V of 0.65 is about equal to 7.3. So this is when I cut out squares of 0.65 on both sides, that's my x value, my maximum volume is the 0.73. Okay? So that's how I'd read that. V of 0.65 equals 7.3. So don't forget about function notation. You're going to try one down at the bottom. So now we've got a new graph. You're going to come up with the domain, the x value at the maximum, the actual maximum volume, and then length of the shorter side. I have one more here I didn't do. So length of the shorter side, remember that comes from the domain. I cut the shorter side in half for that. So to figure out the shorter side, I would have to do 2 times 1.5 and make that 3. So it's just one more kind of cool thing we can find. All right, you're going to go ahead and try this one on your own, and then go back through and unpause it. So our domain's going from here to here. So 0 less than x less than 2.5. My x value at the maximum I would get by like kind of dotting this down. It looks like it's maybe to the right of this line, like slightly more than 1, between 1 and the 1.1. So I'm going to call it about 1.05. My maximum volume is the volume happening at that point, which looks like about 21. So at 1.05, my maximum volume is 21. So this is where it's happening. This is what it is. And don't forget, I could write V of 1.05 equals 21. My volume, when I cut out squares that are 1.05 inches on both sides, is 21 inches cubed. My length of the shorter side, I get by taking this number and doubling it, because that's my shorter side divided by 2. So 2 times 2.5 is going to be 5. So make sure you understand all this stuff. This problem is going to show up over and over and over again, so don't think that you can just ignore it and it will go away. If you have questions about how we're getting our equations, looking at a 3D model might really help in class, but please make sure you ask for help if you need it.